Welcome to the sixth and final installment in our cement soil stabilization series. This installment will focus on 7 case studies, 2 from Pennsylvania and 5 throughout the United States. We will look at 7 case studies that describe projects that have incorporated cement soil stabilization to improve soil properties. Each case study will include project information and detailed discussion of the improvements resulting from the treatment. These case studies are SR-28, multiple locations in western Pennsylvania near Pittsburgh; I-76, Chester County in Pennsylvania; Lower Muscatine Road in Iowa City, Iowa; Los Patrones Parkway, Rancho Mission Viejo, California; Muhlenberg County Airport in Greenville, Kentucky; Des Moines International Airport in Des Moines, Iowa; and the Wilson Middle School and Central Elementary School in San Diego, California. The first case study we will look at is SR-28, the Highland Park Interchange in western PA. The SR-28 Highland Park Interchange Improvement Project was recently awarded the 2024 March of Dimes Transportation, Building, and Construction Transportation Project of the Year. SR-28 is a vital thoroughfare that connects downtown Pittsburgh, Pennsylvania to its northeastern suburbs and beyond. The SR-28 Highland Park Interchange Improvement Project, led by PennDOT and involving multiple partners, addressed bottlenecks and frequent accidents caused by a 2-lane section near the Highland Park Bridge. Key improvements included added travel lanes, ramps, and pedestrian safety features. Despite challenges like narrow corridors, geotechnical issues, and the COVID-19 pandemic, the project was completed successfully in December of 2023, which enhanced traffic flow, safety, and accessibility. This project included open graded subgrade, sandy clay type subgrades, and both wet and dry soil conditions throughout the project. Different stabilization criteria was necessary depending on the existing soil type. The Route 28 corridor, also known as the Allegheny Valley Expressway, provides substantial long-term benefits for both local and regional traffic. With smoother traffic flow, enhanced safety features, and more efficient merging capabilities, Pittsburgh's residents and commuters will experience reduced travel times and fewer bottlenecks. This project is expected to significantly reduce travel delays and improve access to key areas of the city, including the Highland Park area and surrounding neighborhoods. The contractor, Golden Triangle Construction, utilized cement soil stabilization to address some of the geotechnical issues on the project, which aided in maintaining the project's schedule and provided a sound base for the pavement. The second case study is I-76 reconstruction in Chester County. Construction began in the spring of 2023 to widen and reconstruct 4+ miles of the Pennsylvania Turnpike from the Downingtown Interchange, milepost 312 east, to the Valley Ridge Road Bridge, milepost 316, in Upper Euclid, West Pikeland, and Charleston townships in Chester County. The existing 4-lane roadway consisted of 2 12-foot wide travel lanes in each direction, a 10-foot median, and a 12-foot wide outside shoulder. They will be converted into a 6-lane facility with 3 12-foot travel lanes in each direction, a 26-foot median, and a 12-foot wide outside shoulder. The 2023 data showed this stretch of highway typically sees an annual average daily traffic count of 44,000 vehicles. The PA Turnpike Design Consistency Guidelines, published in January of 2025, provides information that was developed by the Pennsylvania Turnpike Commission to be used as a set of guidelines in the design of total reconstruction projects, and is intended to clarify and/or highlight the Pennsylvania Turnpike Commission's design preferences. The document allows for bid results and value engineering proposals on multiple projects, which indicate that cement stabilization of the subgrade is preferred to traditional undercutting and backfilling. Advantages could include the savings, time, predictability, reduced waste size, and a better project. For total reconstruction projects and other projects having extensive subgrade undercut, include special provisions for cement stabilization using cement at an application rate determined during design. Except for the typical exclusion zones around shallow 8 to 18 drainage pipes, structure backfill, and exposed bedrock, the stabilization should be 100% of the project's length and extend from outside of the shoulder to outside of the shoulder. The design should be kept relatively simple, with generally one application rate and depth across the entire project. The Lower Muscatine Road is a case study focused on the construction process. The project was constructed in 2013 in Iowa City, Iowa. The project involved converting a 2-lane road into a 3-lane road. The road included a 12-inch layer of cement solid stabilized material, a 6-inch layer of rock subbase, and a 9-inch layer of concrete pavement. The project was located in both commercial and residential area. Areas that contained shallow buried utilities did not have stabilization treatment due to potential damage. The project contained soil that was highly saturated, and cement soil stabilization was determined to be the best remedy. A cement content of 4% was recommended by the contractor based on previous experience. After review by the Iowa DOT, the recommendation was approved and cement was applied in powder form and mixed with the existing subgrade using a roadway reclaimer. A vibratory sheep's foot roller was used to complete the compaction process and then trimmed with a skid loader. Final compaction was determined using standard Proctor testing and dynamic cone penetration testing, depending on the area being treated. After the compaction was completed, the cement soil stabilized material was allowed to set for 24 hours prior to allowing activity on the treated area. The project was revisited in 2020 and is performing exceedingly well, with only one visible crack located directly above a deep sanitary line. The Los Patrones Parkway was constructed in 2018 in Rancho Mission Viejo, South Orange County, California. This case study is focused on the design process for cement soil stabilization. The Los Patrones Parkway is a 5.5-mile non-toll extension of SR 241 with 2 lanes in each direction. Due to weak and unstable soil, it was determined to utilize cement soil stabilization. The project consisted of 2 million square feet of cement solid stabilized material. The pavement design consisted of 0.2 feet of hot mix asphalt, 0.6 feet of warm mix asphalt, 0.5 feet of aggregate base, and 0.95 feet of cement soil stabilized material. When comparing with the initial pavement design of full depth asphalt, the cost savings from utilizing cement soil stabilization were estimated to be between 30 and 40%. The project required strengths of 300 psi at 7 days, and this consideration provided a 4% application rate of cement. In this instance, a type 2 cement was utilized. 2 Wirtgen reclaimers were used to mix the cement and soil, while a steel wheel roller was used for compaction. This project received the 2018 American Society of Engineers Orange County Branch Project of the Year Award in the Outstanding Transportation Project category. The Muhlenberg County Airport was constructed in 2008. The airport, located in Greenville, Kentucky, was in need of improvements, including a new taxiway. During the design, it was discovered that the soil supporting the 1 to 3 foot taxiway embankment were weak and would create issues with stability. A method was needed to improve the stability of the weak soil, and cement soil stabilization was chosen. Mount Carmel Stabilization Group, Inc. was chosen to perform this modification. The design called for 6% cement content mixed to a depth of 16 inches with a 7-day cure. Before embankment construction could proceed, the cement modification was completed in 2 days. Stability was improved immediately, and embankment construction began 1 week later. Daniel Taylor, the airport manager, was quoted as saying, "It worked out great and appears to have been a great answer for our problem." The Des Moines International Airport project was constructed in 2018. In the summer of 2018, Phase 2 of runway 1331 began reconstruction. This project involved reconstructing approximately 2,500 lineal feet of the runway. The untreated soil under the runway was classified as brown silty clay, an A6 Cl. The sulfate content was 0.19%, according to ASTM-C 1580. To provide a suitable soil base for the pavement structures, the design engineers elected to follow the Federal Aviation Administration specification P-157 to stabilize the soils. This specification requires a soil cement mixture to be designed at a target dosage rate to provide the specified amount of stability in the soil. In this instance, the FAA required 125 psi minimum unconfined compressive strength in the soil cement mixture. During removal of the existing pavement, the geotechnical laboratory, working with the contractor, obtained several subgrade soil samples every 300 lineal feet of the runway. The soil samples were homogenized under laboratory conditions, and cement dosage rates of 2 to 3 and 4% were selected. To keep the unconfined compressive strength near the 125 psi specification requirement, the cement type selected was a Type 1-2. The tests conducted were Atterberg limits, grain size analysis, and Proctor tests on the samples at 3 different dosage rates. Each cement dosage rate yielded an increase in strength of approximately 100 to 300% over the untreated soil. Based on the results of the study, the project utilized a cement dosage rate of 4%, which equates to approximately 38 pounds per square yard of cement. The cement was applied in a dry form. The cement and untreated soil were mixed using a work-gen reclaimer and compacted via a sheep's foot roller and a smooth drum roller. Located in San Diego, California, the Wilson Middle School and Central Elementary School projects were constructed in 2018. The Wilson Middle School was demolished and a new middle school and Central Elementary School were constructed in its place. Upon geotechnical exploration, it was discovered that the site consisted of a substantial amount of expansive soil. The plasticity index of the existing soil ranged from 10 to 36, while the expansion index ranged from 18 to 155, neither of which is ideal for construction. 2 options were considered to improve the site's soil. The first option was to completely remove a portion of the expansive clay soil and replace it with select granular material. The second option was to stabilize the expansive clay soil with either cement or lime. Cement stabilization proved to be the most viable option for remedying the expanse of the soil due to its sustainability, its lower cost versus removal and replacement, and the overall time savings that the option would provide. Decisions to use the cement soil stabilization eliminated over 3,000 truckloads of soil compared to removal and replacement grading operations. A geotechnical evaluation determined that an application rate of 5% cement by dry weight of soil would significantly reduce the plasticity index and the expansion index, allowing the soil to meet the low expansion criteria. The cement was mixed into the soil using a reclaimer, and the subgrade was compacted and trimmed, allowing foundation construction to be completed. Throughout the 6-part series, we have explored the principles, processes, and benefits of cement soil stabilization, following the guidance of the PCA publication. From understanding soil properties and selecting appropriate cement content to mixing, curing, and performance evaluation, we've covered the essential steps to ensure durable and stable soil structures. Cement stabilization remains a proven, cost-effective method for improving soil strength, reducing moisture susceptibility, and enhancing long-term durability for roads, foundations, and embankments. By following best practices, engineers and contractors can achieve more resilient infrastructures with reduced maintenance needs. We hope this series has provided valuable insights into the cement soil stabilization process, equipping you with the knowledge to implement these techniques effectively. If you have any questions or would like to see more content on related topics, let us know, and thank you for watching. If you're interested in more information on cement soil stabilization, please refer to the following: The Guide to Cement Stabilized Subgrade Soils, published by the Portland Cement Association, May 2020. PCA Soil Primer, published by Portland Cement Association in 1992. PennDOT Publication 408, Specifications, October 11, 2024. Soil Cement Laboratory Handbook, published by the Portland Cement Association in 1992. The Guide to Cement-Based Integrated Pavement Solutions, published by the Portland Cement Association in 2014. And the Soil Cement Inspector's Handbook, also published by the Portland Cement Association in 2001. Thank you for joining me today to learn more about cement soil stabilization. This series is presented by the Pennsylvania Aggregates and Concrete Association, the leading voice for the crushed stone, ready-mixed concrete, sand and gravel, and cement industry communities in the state of Pennsylvania. Please feel free to contact PACA for more information related to concrete, aggregates, and/or cement.